Bernhard Riemann was born on September 17, 1826 in Breslauenz, Germany. Although Riemann showed exemplary mathematical abilities from a young age, he decided to become a priest in order to support his family. However, in 1846, his father finally saved enough money to send Bernhard to university, where he began studying mathematics in depth.
At the University of Göttingen, he met Carl Friedrich Gauss, and although Gauss lectured to Riemann, Gauss didn't recognize Riemann's genius, and so they never really studied together.
Riemann went to Berlin University in 1847 to study under several top mathematicians such as Steiner, Jacobi, Dirichlet, and Eisenstein. In particular, Riemann spent a lot of time with Johann Dirichlet, as they shared a strong inner sympathy of like mode of thought.
While in Berlin, Riemann worked out his general theory of complex variables that later formed the foundation of his most important work. Although Riemann was a genius, he often relied on brilliant intuitive reasoning, and he often had trouble absolutely proving his ideas. In 1854, Riemann began his lecture series in which he found the field of Riemannian geometry. He was the first to propose that more than 3 or 4 dimensions were necessary to describe physical reality. His ideas later set the stage for Einstein's theory of relativity. In 1859, he became head of the math department at Göttingen.
In June 1862, Riemann married Elise Koch, who was a friend of his sister's. They had one daughter. In the autumn of the year of his marriage, Riemann was fleeing the Austro-Prussian War when he caught a heavy cold, which led to tuberculosis. He tried to fight the illness by moving to the warmer climate of Italy. While in Italy, he spent time with Enrico Betti and other Italian mathematicians. Riemann died in 1866. Julius Wilhelm Richard Dedekind said this about his death.
His strength declined rapidly, and he himself felt that his end was near, but still, the day before his death, resting under a fig tree, his soul filled with joy at the glorious landscape, he worked on his final work, which unfortunately was left unfinished.
Since Riemann refused to publish incomplete work, a lot of unpublished work was found in his office after his death, and some of his ideas may have been lost forever. But in his 40 years, Riemann made some invaluable contributions to the study of math. His ideas later became major parts of the theories of Riemannian geometry, algebraic geometry, and complex manifold theory. He defined the Riemann integral by means of Riemann sums. Riemann sums use a series of rectangles to define an integral. The length between the bounds is divided into several equal subintervals. Rectangles are drawn with the height being equal to the value of the function at the right side, left side, or midpoint of the subinterval. The combined areas of the rectangle are an approximation of the area on a curve. It is either an underestimation or overestimation depending on the shape of the function.
While Euclidean geometry is the study of flat space, Riemannian geometry at its most basic level is the study of curved surfaces. Riemann geometry can also be used to study higher dimensional spaces, such as points in the universe near black holes and stars, where space is curved. Riemannian geometers look for theories about relationships between curvature, surface, and space, even if they have no practical application. This sphere is a demonstration of one aspect of Riemann geometry. Basically, it's showing that every point on the sphere has a corresponding point on the plane, except the point on the top of the sphere, which we can allow to correspond to any point at infinity on the plane. One of Riemann's other famous ideas was the aptly named Riemann hypothesis. The Riemann zeta function is a complex function. For any complex number, a plus bi, that you plug in, the function will produce another complex number, c plus di. Riemann's hypothesis involved finding zeros of this function, where f of a plus bi equals 0. He called the zeros that occur at negative even integers, -2, -4, -6, and so on, trivial zeros, and all the other ones non-trivial zeros. Riemann's hypothesis proposes that all the other non-trivial zeros occur at 1/2 plus bi for some b.
Where are the zeros of zeta of S? GFB Riemann has made a good guess. They're all on the critical line, stated he, and their density's 1/2 pi log t. This statement of Riemann's has been like a trigger, and many good men with vim and with vigour have attempted to find with mathematical rigour what happens to zeta as mod t gets bigger. The efforts of Landau and Bohr and Cramer, Hardy and Littlewood and Titchmarsh are there. In spite of their effort and skill and finesse in locating the zeros, there's been no success.
The hypothesis has been used in several other mathematical applications, such as the prime number theorem and topology. The Riemann hypothesis has been computationally proved for at least the first 2.4 times 10 to the 12th zeros, but even still, nobody has been able to prove the theory absolutely correct. This is one of math's greatest unsolved problems. In 2000, the Clay Mathematics Institute offered a $1 million prize to whoever could prove the Riemann hypothesis. Interestingly, disproof of the hypothesis does not earn the prize.
Whoa! Big news today. It looks like the 150-year-old Riemann hypothesis, which talks about the zeros of the Riemann zeta function, I'll put a link to some background up here, has finally been proved. Now this is a really big problem in number theory that a lot of people have worked on, especially in the 20th century, because it looks like so many number theory problems are so deceptively easy to understand and so darn difficult to prove. Anyway, I just got an email about this not 15 minutes ago, and I had to tell you guys here on YouTube because I know this is going to be like the biggest news story of the year. I mean, screw the presidential election. You know, that's going to affect the next 8 years, Supreme Court nominations, maybe 20. This is a problem that's 150 years old. And it looks like this guy from Brigham Young University, whose name is Chinese, I won't attempt to pronounce it because I'll just mutilate it. I don't know that much Chinese. Has finally proved it. It's just great. It's an exciting day. Yes!
References to the Riemann hypothesis have showed up in many forms of popular media. In the 2001 movie, A Beautiful Mind, by Ron Howard, the character John Nash is trying to solve the Riemann hypothesis, but he struggles due to the schizophrenia medicine he is taking.
John Nash was one of the most brilliant minds of his generation.
Welcome to Princeton. Who among you will be the next Einstein?
Find a truly original idea, and it's the only way I will ever distinguish myself. It's the only way I will ever matter.
He saw the world.
Where's Nash?
Out there, looking for his original idea.
In ways that no one could imagine.
This flies in the face of 150 years of theory.
Congratulations, John. It's the achievement of a lifetime.
In Season 1 of the television crime drama Numbers, the character Ethan's daughter is kidnapped because he is close to solving the Riemann hypothesis, which would allow the criminals to break all internet security.
FBI agent plus a math genius. The new season of Numbers will change the way you think about crime solving.
It's a plan for an assassination.
Count on it.
Hey! These groupings, they're types of killings.
He's trying to outthink us, we're going to be trying to outthink him.
Drop it! The game has changed completely.
How did you learn all this stuff about assassination?
If I told you that, I'd have to kill you.
Seriously?
Seriously.
Numbers season premiere, Friday, September 23rd.
Despite the brevity of his life, Bernhard Riemann was a mathematical genius, and his work still remains relevant today.